Welcome to Loops and Loops, your gateway to the captivating world of neural networks. Join us as we embark on an exhilarating journey through the realm where artificial intelligence meets the intricacies of the human brain. From deep learning algorithms to convolutional networks, neural networks are revolutionizing industries and transforming the way we interact with technology. Whether you're an AI enthusiast or just curious about the mechanics of intelligent systems, you're in for an enlightening experience. So tighten your loops, expand your understanding, and let's dive into the mesmerizing world of neural networks together. A neural network is a computational model inspired by the structure and function of the human brain. It consists of interconnected nodes called neurons organized into layers, through which data flows, allowing the network to perform complex tasks like pattern recognition, classification, and regression. Neural networks mimic the human brain by using interconnected neurons to process and transmit information. Like the brain, they can learn from experience, adapt to new inputs, and improve performance over time. The basic components of a neural network include neurons, weights, biases, activation functions, and layers. Neurons receive input signals, apply weights and biases, and pass the result through an activation function to produce an output. These outputs are then passed to other neurons in the network, allowing information to flow through the network. Neurons in a neural network are connected through weighted connections, which determine the strength of the connection between neurons. These weights are adjusted during the learning process to optimize the network's performance. The input layer of a neural network receives input data and passes it to the subsequent layers for processing. It contains one neuron for each feature or input variable. The output layer of a neural network produces the final output, or prediction based on the processed input data. It contains one neuron for each possible output or class in a classification task. Information flows through a neural network in a forward pass, starting from the input layer, passing through the hidden layers, and culminating in the output layer where the final prediction or output is generated. The activation function in a neural network determines the output of a neuron based on its input. It introduces nonlinearity into the network, enabling it to learn complex patterns and relationships in the data. Neural networks learn from data through a process called training, where they adjust their weights and biases to minimize the difference between predicted and actual outputs. This is typically done using optimization algorithms like gradient descent. Backpropagation is an algorithm used to train neural networks by computing the gradient of the loss function with respect to the network's parameters. It involves propagating the error backward through the network and adjusting the weights and biases accordingly to minimize the error. Supervised learning in neural networks involves training the network on labeled data, where each input is associated with a corresponding target output. The network learns to map inputs to outputs by minimizing the difference between predicted and actual outputs. Unsupervised learning in neural networks involves training the network on unlabeled data, where the network learns to extract meaningful patterns or features from the data without explicit supervision. Reinforcement learning in neural networks involves training the network to make sequential decisions by interacting with an environment and receiving feedback in the form of rewards or penalties. The network learns to maximize cumulative rewards over time by exploring different actions and learning from the consequences. The loss function in a neural network is a mathematical measure that quantifies the difference between the predicted output of the network and the actual output or ground truth. It represents how well the network is performing on a given task, such as classification or regression. The loss function is used in training a neural network to guide the optimization process. During training, the network adjusts its parameters, such as weights and biases, to minimize the value of the loss function. This is achieved through an optimization algorithm like gradient descent. Gradient descent is an optimization algorithm used to minimize the loss function and train neural networks. It works by iteratively adjusting the parameters of the network in the direction of the steepest descent of the loss function with respect to those parameters. This process continues until the algorithm converges to a minimum of the loss function. Training neural networks comes with several challenges, including vanishing gradients, exploding gradients, overfitting, underfitting, and computational complexity. These challenges can affect the network's ability to learn and generalize from the training data. Overfitting occurs when a neural network learns to perform well on the training data, but fails to generalize to new unseen data. It can be prevented by techniques such as regularization, dropout, and early stopping, which aim to reduce the complexity of the model and improve its ability to generalize. Underfitting, on the other hand, occurs when a neural network is too simple to capture the underlying patterns in the data. It can be addressed by increasing the complexity of the model, adding more layers or neurons, or using more sophisticated architectures. Common types of neural networks include feed-forward neural networks, recurrent neural networks, convolutional neural networks, generative adversarial networks, long short-term memory networks, and gated recurrent unit networks. Each type has its unique architecture and is suited for different tasks. A feed-forward neural network is the simplest type of neural network where information flows in one direction, from input to output, without any loops or cycles. It's commonly used for tasks like classification and regression. A recurrent neural network is designed to handle sequential data by introducing connections between neurons that form loops, allowing information to persist over time. RNNs are commonly used for tasks like time series prediction and natural language processing. A convolutional neural network is specialized for processing grid-like data, such as images, by applying convolutional operations to extract hierarchical features. Convolutional neural networks are widely used in image recognition and computer vision tasks. A generative adversarial network consists of two neural networks, a generator and a discriminator, that are trained together in a competitive manner. Generative adversarial networks are used for generating new data samples, such as images or text, that resemble the training data. Long short-term memory networks are a type of recurrent neural network designed to capture long-term dependencies in sequential data by introducing memory cells with gating mechanisms. Long short-term memories are commonly used for tasks like speech recognition and language translation. Gated recurrent unit networks are another type of recurrent neural network that simplifies the architecture of long short-term memory networks while retaining similar capabilities. GRUs are often used in scenarios where computational resources are limited or simpler models are preferred. Neural networks are used in image recognition by processing pixel data through layers of neurons to extract features and make predictions about the content of images. They can identify objects, classify images, and even generate new images. In natural language processing, neural networks are used to process and understand human language by converting text data into numerical representations that can be processed by the network. They are used for tasks such as language translation, sentiment analysis, and text generation. Neural networks are employed in speech recognition by processing audio data to identify and interpret spoken words. They analyze patterns in sound waves and convert them into text, allowing devices like smartphones and virtual assistants to understand and respond to human speech. In autonomous vehicles, neural networks play a crucial role in interpreting sensor data from cameras, LiDAR, and radar systems to perceive the vehicle's surroundings. They help in tasks such as object detection, lane detection, and pedestrian recognition, enabling the vehicle to make decisions and navigate safely. In medical diagnosis, neural networks analyze patient data such as medical images, genetic information, and clinical records to assist healthcare professionals in diagnosing diseases and conditions. They can detect abnormalities in medical images, predict disease risk factors, and provide personalised treatment recommendations. In financial forecasting, neural networks analyse historical market data and economic indicators to predict future trends in stock prices, exchange rates, and other financial instruments. They help investors and financial institutions make informed decisions about investments and risk management. Recommender systems utilise neural networks to analyse user preferences and behaviour to recommend personalised products, services, or content. They power recommendation engines on e-commerce platforms, streaming services, and social media platforms, enhancing user experience and engagement. Neural networks are integrated into robotics to enable tasks such as object recognition, motion planning, and control in robotic systems. They allow robots to perceive their environment, make decisions, and adapt to changes autonomously, enhancing their capabilities in various applications. In drug discovery, neural networks analyse chemical and biological data to predict the properties and activities of molecules, aiding in the development of new drugs and therapies. They accelerate the drug discovery process by screening potential candidates and optimizing drug design. Anomaly detection systems utilize neural networks to identify unusual patterns or deviations from normal behavior in data, such as network traffic, manufacturing processes, or financial transactions. They help detect and prevent fraudulent activities, equipment failures, or security breaches. Virtual assistants like Siri, Alexa, and Google Assistant employ neural networks to understand and respond to user queries and commands. They process natural language input, extract relevant information, and generate appropriate responses, providing users with personalized assistance and information. Sentiment analysis involves using neural networks to analyze text data, such as social media posts or customer reviews, to determine the sentiment or emotions expressed. It helps businesses understand public opinion, customer feedback, and trends, enabling them to make informed decisions and improve products or services. Neural networks are utilised in fraud detection systems to identify fraudulent transactions or activities by analysing patterns and anomalies in financial data. They help financial institutions detect and prevent fraudulent behaviour, protecting customers and mitigating financial losses. In game playing, neural networks are employed to develop intelligent agents that can play games such as chess, Go, or video games. They learn to make strategic decisions and adapt to different game scenarios, competing against human players or other AI opponents. Weather forecasting models leverage neural networks to analyse meteorological data, such as temperature, humidity, and wind patterns, to predict weather conditions and patterns. They help meteorologists make forecasts about future weather events and phenomena, aiding in disaster preparedness and planning. In genomics, neural networks analyse genetic sequences and biological data to study gene expression, protein interactions, and disease mechanisms. They help researchers understand complex biological systems, identify genetic markers, and develop personalised medicine and treatments. Customer segmentation involves using neural networks to group customers based on similarities in behaviour, demographics, or preferences. They help businesses tailor marketing strategies, product recommendations, and customer experiences to specific customer segments, improving customer satisfaction and retention. Neural networks play a crucial role in personalised medicine by analysing individual patient data, such as genetic information, medical history, and lifestyle factors, to tailor treatment plans and interventions. They help healthcare professionals predict disease risk, recommend personalised therapies, and optimise treatment outcomes based on patient-specific characteristics. In social network analysis, neural networks analyse social media data and online interactions to identify patterns, communities, and influential users. They help researchers understand social dynamics, detect trends, and predict user behaviour, aiding in targeted marketing, content moderation, and social network optimization. Text generation involves using neural networks to generate human-like text based on input prompts or existing text data. They are employed in applications such as chatbots, virtual assistants, and content generation tools, producing natural and coherent text responses or content. Autonomous drones utilize neural networks to process sensor data and make decisions in real time, enabling tasks such as navigation, obstacle avoidance, and object tracking. They help drones operate autonomously in various environments, including surveillance, agriculture, and delivery. Content recommendation systems use neural networks to analyze user preferences and behavior to recommend personalized content, such as articles, videos, or products. They enhance user engagement and satisfaction by providing relevant and timely recommendations tailored to individual interests. Emotion recognition involves using neural networks to analyze facial expressions, voice patterns, or text data to identify and interpret human emotions. They are employed in applications such as customer service, healthcare, and entertainment, enabling systems to understand and respond to user emotions. Object detection systems utilize neural networks to identify and localize objects within images or videos. They are employed in various applications, including surveillance, autonomous vehicles, and medical imaging, enabling systems to recognize and track objects of interest. Machine translation involves using neural networks to translate text or speech from one language to another. They analyze linguistic patterns and semantic meaning to produce accurate and fluent translations, facilitating communication and information exchange across languages. Face recognition systems use neural networks to analyze facial features and patterns to identify individuals from images or video footage. They are employed in security, law enforcement, and access control systems, enabling biometric authentication and identity verification. Autonomous navigation systems utilize neural networks to process sensor data and make decisions for navigating vehicles or robots in dynamic environments. They help systems plan routes, avoid obstacles, and adapt to changing conditions, enabling safe and efficient navigation. In cybersecurity, neural networks analyze network traffic, system logs, and user behavior to detect and prevent cyber threats such as malware, phishing, and unauthorized access. They help identify anomalies, predict potential attacks, and strengthen defense mechanisms to protect digital assets and data. Customer churn prediction involves using neural networks to analyze customer data and predict the likelihood of customers leaving a service or subscription. They help businesses identify at-risk customers, implement targeted retention strategies, and improve customer loyalty and satisfaction. Energy forecasting systems utilize neural networks to analyze historical energy consumption data and predict future demand or generation patterns. They help energy companies optimize resource allocation, plan infrastructure investments, and improve energy efficiency and sustainability. Wildlife conservation efforts utilize neural networks to analyze ecological data, such as satellite imagery, camera trap photos, and acoustic recordings to monitor and protect endangered species and habitats. They help researchers track animal populations, detect illegal activities, and inform conservation strategies and policies. Neural networks are utilized in agriculture to optimize crop yield, predict crop diseases, and monitor soil conditions. By analyzing data from sensors, satellites, and drones, neural networks can provide farmers with valuable insights into crop health, water usage, and pest management, allowing for more efficient and sustainable farming practices. In supply chain optimization, neural networks are employed to forecast demand, optimize inventory levels, and improve logistics efficiency. By analyzing historical sales data and market trends, neural networks can help businesses streamline their supply chain operations, reduce costs, and enhance customer satisfaction through timely deliveries and optimized inventory management. Traffic management systems utilize neural networks to analyze traffic patterns, predict congestion, and optimize traffic flow. By processing data from sensors, cameras, and GPS devices, neural networks can provide real-time insights to traffic controllers, enabling them to adjust traffic signals, reroute vehicles, and alleviate congestion in busy urban areas. In music generation, neural networks are used to compose, arrange, and produce music autonomously. By analyzing patterns in existing music compositions, neural networks can generate new melodies, harmonies, and rhythms, offering musicians and composers new creative possibilities and inspiration. Real-time bidding platforms use neural networks to analyze user behavior and predict ad performance in milliseconds. By processing vast amounts of data about user preferences and browsing history, neural networks can help advertisers bid on ad placements more effectively, maximizing their return on investment and reaching their target audience more efficiently. Virtual reality applications utilize neural networks to create immersive experiences and realistic simulations. By processing sensory data from virtual environments and user interactions, neural networks can enhance the realism and interactivity of virtual reality experiences, enabling users to engage with digital content in more immersive ways. Augmented reality systems use neural networks to overlay digital information onto the physical world in real time. By analyzing the user's surroundings and context, neural networks can enhance the accuracy and relevance of augmented reality content, offering users valuable information and interactive experiences in their everyday environment. Drug response prediction involves using neural networks to analyze genetic data and predict how individuals will respond to different medications. By identifying genetic markers associated with drug efficacy and adverse reactions, neural networks can help healthcare providers personalize treatment plans and improve patient outcomes. Network intrusion detection systems utilize neural networks to identify and mitigate cyber threats in computer networks. By analyzing network traffic patterns and detecting anomalous behavior, neural networks can detect and respond to potential security breaches, protecting sensitive data and preventing cyber attacks. Sentiment analysis involves using neural networks to analyze text data and extract sentiment or emotions expressed by users. By processing social media posts, customer reviews, and other text data, neural networks can identify positive, negative, or neutral sentiments, enabling businesses to understand customer feedback and sentiment trends. Customer service automation systems use neural networks to automate repetitive tasks and streamline customer interactions. By analyzing customer inquiries and dialogues, neural networks can provide automated responses, route inquiries to the appropriate department, and improve the efficiency of customer service operations. Content moderation platforms utilize neural networks to detect and remove inappropriate or harmful content from online platforms. By analyzing images, videos, and text data, neural networks can identify content that violates community guidelines or poses risks to users, helping to maintain a safe and positive online environment. Image captioning involves using neural networks to generate descriptive captions for images automatically. By analyzing the content and context of images, neural networks can generate natural language descriptions that accurately describe the visual content, enabling accessibility and enhancing user experience in applications such as social media and image search. Content creation tools use neural networks to assist users in generating various types of content, such as articles, artwork, or music. By analyzing user input and existing content, neural networks can provide suggestions, generate drafts, and assist users in the creative process, offering inspiration and support in content creation endeavors. Supply chain management systems leverage neural networks to optimize inventory levels, forecast demand, and improve operational efficiency. By analyzing data from suppliers, manufacturers, and distributors, Neural networks can help businesses reduce costs, minimize stockouts, and streamline supply chain operations, enhancing overall performance and competitiveness. Neural networks are applied in social media analytics to analyze user behavior, sentiment, and trends across various platforms. You're processing vast amounts of social media data. Neural networks can identify patterns, detect emerging topics, and predict user engagement, helping businesses understand and leverage social media for marketing, customer engagement, and brand management purposes. In wildlife monitoring, neural networks are used to analyze camera trap images, satellite data, and acoustic recordings to track and identify animal species, monitor habitat changes, and assess biodiversity. By automatically classifying and recognizing wildlife patterns, neural networks enable researchers and conservationists to collect data more efficiently and make informed decisions about wildlife conservation efforts. Urban planning utilizes neural networks to analyze urban infrastructure, traffic patterns, and demographic data to optimize city design and development. By processing data from sensors, GPS devices, and urban databases, neural networks can help urban planners identify areas for improvement, predict future population growth, and plan for sustainable urban development. Manufacturing optimization employs neural networks to optimize production processes, improve product quality, and reduce costs in manufacturing industries. By analyzing sensor data, production logs, and quality control metrics, neural networks can identify inefficiencies, predict equipment failures, and optimize manufacturing workflows, enhancing productivity and profitability. Language modeling involves using neural networks to generate human-like text or speech in natural language processing tasks. By analyzing large corpora of text data, neural networks can learn the syntactic and semantic patterns of human language, enabling applications such as machine translation, text generation, and speech recognition. Product recommendation systems leverage neural networks to analyze user preferences, purchase history, and browsing behavior to recommend relevant products or services. By processing user interactions and feedback, neural networks can personalize recommendations, improve user experience, and increase sales for e-commerce platforms and online retailers. Fault detection systems use neural networks to monitor industrial equipment, detect anomalies, and predict equipment failures in real time. By analyzing sensor data and historical performance, neural networks can identify deviations from normal operating conditions, enabling proactive maintenance and minimizing downtime in industrial settings. Data compression techniques employ neural networks to compress large data sets into smaller representations while preserving essential information. By learning efficient representations of data, neural networks can reduce storage space, accelerate data transmission, and optimize memory usage in various applications, including image and video compression. Medical imaging utilizes neural networks to analyze and interpret medical images, such as X-rays, MRIs, and CT scans for diagnostic purposes. By extracting features and patterns from image data, neural networks can assist radiologists in detecting abnormalities, diagnosing diseases, and guiding treatment decisions, improving patient care and outcomes. Autonomous vehicles employ neural networks to perceive the surrounding environment, detect obstacles, and make driving decisions in real time. By processing sensor data from cameras, LiDAR, and radar systems, neural networks can recognize objects, predict their movements, and navigate safely in complex traffic scenarios, enabling autonomous driving technology. Facial recognition systems utilize neural networks to identify and verify individuals based on facial features captured in images or video footage. By analyzing facial landmarks and patterns, neural networks can match faces against a database of known identities, enabling applications such as biometric authentication, surveillance, and access control. Weather prediction employs neural networks to analyze meteorological data, satellite images, and atmospheric models to forecast weather patterns and phenomena. By learning complex relationships between weather variables, neural networks can predict future weather conditions, provide early warnings for severe weather events, and support decision-making in meteorology and climate science. Gaming utilizes neural networks for various purposes, including character animation, game design, and player behavior prediction. By simulating virtual environments, learning player preferences, and generating realistic game elements, neural networks enhance the immersion and realism of video games, offering engaging and interactive gaming experiences. Speech synthesis involves using neural networks to generate human-like speech from text input. By learning the prosody, intonation, and pronunciation rules of spoken language, neural networks can synthesize natural-sounding speech for applications such as virtual assistants, voice assistants, and automated customer service systems. Chatbots utilize neural networks to understand and generate natural language responses in conversational interactions with users. By analyzing text input, learning from previous conversations, and generating contextually relevant responses, neural networks enable chatbots to provide personalized assistance, answer questions, and engage users in natural language conversations. Neural networks are employed in autonomous drones to navigate, identify obstacles, and make decisions independently. By processing data from onboard sensors like cameras and LiDAR, neural networks can recognize objects, plan flight paths, and avoid collisions, enabling drones to operate safely and efficiently in various environments, such as surveillance, agriculture, and package delivery. Credit scoring utilizes neural networks to assess creditworthiness and predict the likelihood of loan defaults based on borrower profiles and financial histories. By analyzing vast amounts of credit-related data, neural networks can identify patterns, assess risk levels, and automate the credit evaluation process, helping lenders make informed decisions and manage credit risk effectively. Customer segmentation employs neural networks to group customers based on shared characteristics, preferences, and behaviors. By analyzing customer data such as demographics, purchase history, and online interactions, neural networks can identify distinct customer segments, tailor marketing strategies, and personalize product recommendations, enhancing customer engagement and satisfaction. Predictive maintenance utilizes neural networks to forecast equipment failures and schedule maintenance activities proactively. By analyzing sensor day-to-day equipment performance metrics and maintenance records, neural networks can detect anomalies, predict potential failures, and optimize maintenance schedules, minimizing downtime and reducing maintenance costs in industrial settings. Document analysis involves using neural networks to extract, classify, and analyze information from documents such as invoices, contracts, and forms. By processing text, images, and structured data, neural networks can automate document processing tasks, extract relevant information, and improve document management efficiency in various industries, including finance, legal, and healthcare. Stock trading employs neural networks to analyze market data, identify trading patterns, and make investment decisions. By processing historical stock prices, news articles, and market indicators, neural networks can predict price movements, identify trading opportunities, and optimize trading strategies, enabling traders to make informed investment decisions and maximize returns. Fraud detection utilizes neural networks to identify fraudulent activities and prevent financial losses in banking, e-commerce, and other industries. By analyzing transaction data, user behavior, and historical fraud patterns, neural networks can detect anomalies, flag suspicious transactions, and mitigate fraud risks, protecting businesses and customers from fraudulent activities. Network security employs neural networks to detect and mitigate cybersecurity threats such as malware, phishing attacks, and network intrusions. By analysing network traffic, log files, and security events, neural networks can identify abnormal behaviour, detect potential threats, and enhance threat detection capabilities, strengthening network defences and protecting sensitive data. Personalised medicine utilises neural networks to analyse genetic data, patient medical records, and clinical outcomes to tailor treatment plans and predict disease risks. By processing large-scale genomic data and healthcare records, neural networks can identify genetic markers, predict treatment responses, and optimise personalised healthcare interventions, improving patient outcomes and healthcare efficiency. Music recommendation systems use neural networks to analyse user preferences, listening habits, and music features to generate personalised playlists and recommendations. By processing music metadata, user interactions, and audio features, neural networks can recommend relevant songs, discover new artists, and enhance user engagement in music streaming platforms and applications. Investment analysis employs neural networks to analyse financial data, economic indicators, and market trends to evaluate investment opportunities and risks. By processing historical market data, company financials, and macroeconomic indicators, neural networks can predict asset prices, identify trading strategies, and support investment decision-making in finance and investment management. Advertising employs neural networks to analyse user demographics, interests, and online behaviour to target ads and optimise campaigns. Processing and impressions, click-through rates, and conversion data, neural networks can identify target audiences, personalise ad content, and improve ad performance, maximising advertising effectiveness and return on investment. Customer retention strategies utilise neural networks to analyse customer behaviour, preferences, and feedback to identify at-risk customers and implement targeted retention campaigns. By processing customer data, purchase history, and interaction patterns, neural networks can predict customer churn, segment customer groups, and personalise retention efforts, improving customer loyalty and retention rates for businesses. Neural networks are harnessed in text summarization to condense large volumes of text into concise summaries. By analysing the content and structure of documents, neural networks can identify key information, extract important sentences, and generate summaries that capture the essence of the original text, facilitating efficient information retrieval and comprehension. Knowledge discovery utilises neural networks to uncover valuable insights and patterns from large datasets. By processing diverse data sources and extracting hidden relationships, neural networks can identify trends, discover hidden patterns, and generate actionable insights, empowering decision-making and innovation in various fields such as healthcare, finance, and research. Sentiment classification employs neural networks to analyse text data and classify sentiment polarity, such as positive, negative, or neutral. By processing textual features, linguistic patterns, and contextual clues, neural networks can accurately categorise text sentiments, enabling businesses to gauge customer opinions, sentiment trends, and brand perception, informing marketing strategies and customer engagement efforts. Content filtering utilises neural networks to personalise content recommendations and filter out irrelevant or inappropriate content. By analysing user preferences, browsing behaviour, and content features, neural networks can recommend relevant content, detect spam or offensive material, and improve content curation and moderation in online platforms and applications. Speech recognition employs neural networks to convert spoken language into text. By processing audio signals, phonetic features, and language patterns, neural networks can transcribe speech accurately, enabling voice-controlled interfaces, virtual assistants, and automated transcription services, enhancing accessibility and user experience in various applications. Event detection utilises neural networks to identify and classify events or anomalies in data streams. By analysing sensor data, network traffic, or social media feeds, Neural networks can detect unusual patterns, identify significant events, and trigger alerts or responses in real time, supporting applications such as surveillance, cybersecurity, and predictive maintenance. Traffic prediction employs neural networks to forecast traffic conditions, congestion levels, and travel times. By analysing historical traffic data, weather conditions, and transportation patterns, neural networks can predict future traffic trends, optimise route planning, and improve traffic management and urban mobility. Market analysis utilises neural networks to analyse financial data, market trends, and investor sentiment to predict asset prices and market movements. By processing historical market data, news articles, and economic indicators, neural networks can identify trading opportunities, forecast market trends, and support investment decision-making in finance and trading. Recommendation systems utilize neural networks to analyze user preferences, browsing behavior, and content features to deliver personalized recommendations and suggestions. By processing user interactions and content metadata, neural networks can recommend relevant products, articles, or media content, enhancing user engagement and satisfaction in e-commerce, media, and content platforms. Demand forecasting employs neural networks to predict future demand for products or services based on historical sales data, market trends, and external factors. By analysing sales patterns, economic indicators, and consumer behaviour, neural networks can forecast demand accurately, optimise inventory management, and improve supply chain efficiency in retail and manufacturing. Email classification utilises neural networks to categorise incoming emails into different folders or labels based on their content or purpose. By analysing email content, sender information, and metadata, neural networks can classify emails into categories such as primary, social, promotions, or spam, improving email organisation and productivity for users. Sales prediction employs neural networks to forecast future sales volumes or revenues based on historical sales data, market trends, and promotional activities. By analysing sales patterns, customer demographics, and marketing campaigns, neural networks can predict sales outcomes, optimise pricing strategies, and support sales planning and forecasting in retail and sales management. Risk assessment utilises neural networks to evaluate and quantify risks associated with various activities, investments, or decisions. By processing relevant data sources and identifying risk factors, neural networks can assess risks accurately, prioritise risk mitigation measures, and inform decision-making processes in finance, insurance, and project management. Quality control employs neural networks to detect defects, anomalies, or deviations from desired standards in manufacturing processes or product quality. By analysing sensor data, images, or inspection results, neural networks can identify quality issues, classify defects, and automate quality control inspections, ensuring product consistency and compliance with quality standards. Process optimization utilises neural networks to improve efficiency, productivity, and performance in industrial processes or business operations. By analysing process data, workflow patterns, and performance metrics, neural networks can identify bottlenecks, optimise resource allocation, and automate decision-making processes, enhancing productivity and competitiveness in various industries. As we wrap up today's exploration of neural networks, we hope you've gained valuable insights into the power and potential of these remarkable computational models. Don't forget to share and subscribe to Loops and Loops for more captivating content on artificial intelligence and machine learning. Let's continue to loop in new knowledge, push the boundaries of what's possible with neural networks, and shape a future where intelligent systems enhance our lives in unimaginable ways. Until next time, keep those loops tight, keep learning, and keep dreaming big. Thank you for joining us on this exciting journey.